Welcome to qnawire.
We're asked to find what height above the surface of the Earth, so h here, a satellite needs to be so that it's always above the same point on the Earth. So that's basically asking us then for the satellite to be in geosynchronous orbits so that it and the Earth have the same period of rotation. So if that's true, then there'll always be this constant line between the Earth and the satellite, so it won't be moving with respect to the Earth. So that tells us that the period for this motion needs to be 24 hours, so just one day, so that's how long it takes Earth to rotate once. And so we want to convert that to seconds for use in our calculations. So doing that, we should get 8.64 times 10 to the fourth seconds. So now we want to figure out what this h needs to be. So to start, for circular motion, circular orbit, we know the velocity of the orbit should always be the square root of g m over r. So m here would be the mass of the Earth, and then r would be this total distance from the center of the Earth out to over here, so re plus h in this case. Um, and so then we also know that the period of motion would be given by 2 pi r. So again, the same r of this total distance here. So the circumference of the motion divided by the velocity. And so if we can figure out r from these equations, then we'd be able to find what this h is. So to start, we know the value of t here. We know t is 8.64 times 10 to the fourth. So let's substitute in this expression for v into our equation for t. So we'd have then t equals 2 pi r, and then divided by v, so we just flip this. So we'd have then square root of r over g me. And then we can simplify that to 2 pi r to the 3/2 over square root of g me. So now we can just solve for r, and then we should be able to calculate, because I think we'll know all the other terms then. So if we square each side and then take the cube root and move all these terms around, we should get then that r will be t squared g me over 4 pi squared. And then that whole thing is to the 1/3. So t squared is just this t that we found up here. We look up mass of the Earth, we know g. So we compute this as 4.23 times 10 to the 7th meters. But remember, that's this total r here. So we just want h. So h will be r minus re. And so when we do that, we'll get 3.59 times 10 to the 7th meters. So that'll be the height that any satellite or any object in orbit will always have a period of 24 hours. So it'll always stay above the same point on Earth. So then for part B, we're asked to explain why a radio wave, or really any sort of signal or line of sight, can't be made between the satellite and kind of the upper part of the Earth here. So if we say the satellite is always in line with the equator, we can see then just drawing a line from the satellite that'll be tangent to the Earth. So like that. There's going to be a little part up here that's sort of inaccessible by this line. So we can draw out an angle here. And so that's kind of the highest angle that the satellite has a line of sight to. So we could call that theta. And so they've told us that this theta is 81.3 degrees. So anything higher up on the Earth at an angle than that would not be able to communicate with the satellites, at least directly. If they hadn't given us this angle, though, we could find this with some trigonometry pretty quickly. So this is a right angle. So that means then we can say that cosine of theta would be this adjacent side over this hypotenuse. So the adjacent side is just the radius of the Earth, and the hypotenuse is just that r, the total distance from the center of the Earth to the satellite that we found. And so theta then would be inverse cosine of that. And so if we calculate that out, then we would get 81.3 degrees.